Okay, so today we're going to talk about reinforcement learning. So till now we've discussed supervised learning methods like neural networks and unsupervised learning methods like k-means clustering and the EM algorithm, and like the countless possibilities of the things you can do with those algorithms. And today, as I mentioned earlier, we're going to focus on reinforcement learning. So I'm going to start by giving a very high-level idea of what RL is, and then talk about why this even exists and why the idea of reinforcement learning is so powerful. Um, so reinforcement learning is a system that fundamentally is based on the principle of punishment and reward. So if an algorithm makes a good decision, like if it's playing a game and it does something that increases its score, it's given a reward. And if it does something detrimental, then it's given a negative reward. And of course, the goal of the algorithm is to maximize rewards. It's a lot like reinforcement learning when it comes to humans during the course of their entire life. Like if we do something that is beneficial, we get positive rewards. If we do something bad, we get punishment. So anyway, so diagrammatically, it's nice to visualize concepts like this. So we have an agent. That agent takes an action, and that action has some effect on the environment. So because of that action, that environment changes, and that new state then goes to the agent. So now the agent knows what change is brought about in the environment based on that action, and the agent also gets knowledge of a reward reward based on the action that it took. This will make a little bit more sense when we talk about an example later on. But yeah, so essentially you have an agent, it takes an action, it makes a move, it does something that goes into the environment, and that so if it's something like chess, you move, the action is to move a pawn one step ahead. So that goes to the environment, that causes a change in game state now, where the board is what it was before, except one pawn is now ahead. So now the agent gets that new game state, and it also gets a reward. So like if you have a function that evaluates how good of a state the board is for you, like if you have good positioning, etc. If this move gets you in a better position, then you get a positive reward, otherwise a negative reward. Or if your move killed another what do you call it, piece of the opponent, then you could get a positive reward, something like that. Anyway, so at a very high level, basically that is what reinforcement learning is. So why does something like this exist, and why is the idea of reinforcement learning so powerful? So to answer that question, I'm going to take an example of a game. So the simplest game I could think of was Brick Breaker. So I'll actually just explain Brick Breaker really quickly for those of you who don't know. So what the game is essentially you have this pad. This pad, so the goal is to not let the ball fall down. So if the ball is going in the direction of this arrow, you would move your pad to the right so that the ball hits the pad, bounces off, and goes back up. And the goal is to hit these blocks, and every time you hit the block, like say you hit this green one, the block goes away, and you have to clear all of the blocks essentially. So that's Brick Breaker, really simple game. Now, how would you make an algorithm play a game like this? Now, you could use a neural network. Now, to do that, you would have to get a person to play the game for a really long time, and then take screenshots of this game and feed that information into a neural network, and whatever action the person was taking, those would be like the targets for the neural network. So like if this is a screenshot that you sent to the neural network, and let's just, for example, say the ball was moving this way, the person would, like the human player, would move this to the right. So in a scenario like this, the target for the neural network would be the right arrow key. Like it would learn to press right in this scenario, left in a scenario when the ball is going to the left, etc. And it would learn like that. Of course, it doesn't have to be screenshots. Like you could send the the position of the ball, the position of this, and the position of the bricks, or like data in whatever way you want. But like there would be a component of immense data collection and a lot of human effort that goes into it to play the game for a really long time, etc. And this can be, well, really time consuming and just very inefficient to do. But most importantly, since the algorithm is learning from a human, it will never be better than the human. And this is a severe limitation. And so an algorithm like this would be limited by human capability. But if you take it in a very, in like a broad sense, this type of intelligence would be limited by human level intelligence. It would never be able to surpass a human or do better than a human in a game, or whatever scenario you're using this for. And this is where reinforcement learning comes into play. So instead of having like the human actions as targets, the network and that decides the moves, and in the case of reinforcement learning, this network is called the policy network. It's just given a positive or a negative reward based on its actions. It's not given like the human action targets. So and the reward doesn't even have to be given immediately. Just like in real life, like if you take an action right now, you can get a reward or a punishment for it, like or consequences for it just down the line. Similarly, you can have rewards that come in due course in reinforcement learning. But anyway, so so this way, a programmer, like as a programmer, you only have to design like the environment you're playing in and the reward system. And like for a game like this, an example could be every time the ball hits a brick, you get +1 point. Every time the ball goes down, like the pad misses the ball, you get -1 point. And just something as simple as that would over time learn to play the game really well. And I mean, if you wanted to make it more efficient, like if you wanted to make it an actually good brick breaker player, you could make it like -1 point for every 10 seconds that the game is played. That way, the algorithm would be incentivized to finish the game faster. But anyway, yeah. So that's why the idea is so powerful, and this way, like it's a lot less effort because you don't have to have someone play the game for a long time and do the whole data collection, data cleanup, like just a bunch of things when it comes to like having large data for a neural network. But most importantly, this method is not limited by human ability. And this actually might be really surprising for a lot of you, hearing that human ability or human intelligence can limit machine intelligence and machine ability. But actually, a good example of this would be AlphaGo and AlphaZero. So what AlphaGo is, it's a program that plays the game of Go. So Go is a board game, and it's an incredibly complex board game. So we learned about Minimax before, how you can just evaluate different game states and do that for the entire, like every possible game state, and then choose the best move. But for something like Go, that's absolutely impossible because the number of game states in the game of Go is 45 times the number of atoms in the entire universe. That's that's something I don't think we'll ever be able to even comprehend. And that's why it's really that's why you can't like have a brute force sort of an algorithm. Like it's a game that's really hard for an algorithm to play. Like it requires intelligence, it requires creativity. Anyway, that's a whole other topic we can talk about. But what AlphaGo was, that was an algorithm that was trained based on like they had a lot of training data from humans playing the game of Go, and it was trained on the best of humans playing the game, and it did beat the best Go player. It did play Go at a superhuman level, but then DeepMind came out with AlphaZero, and AlphaZero never saw a human play the game. AlphaZero just played with itself, like it trained itself. So AlphaZero was an algorithm that played Go using reinforcement learning and a bunch of other things, but at its core, like the idea was reinforcement learning. And so two algorithms would play against each other. They would get better, they would keep playing against each other and get better and better. And AlphaZero actually beat AlphaGo 100-0 in a series of Go games. So it's just a nice example of how humans can, in many cases, be the limiting factor. And that's why reinforcement learning is such a powerful tool. Agent 57 was another one of sorry, Agent 57 was another one of DeepMind's algorithms that played that mastered all 57 Atari games, and it played, I think, most of them to a superhuman level, and it would never be able to play at a superhuman level if a human trained it how to, like, if it was trained on human gameplay. So yeah, at a very high level, that's what reinforcement learning is. In this video, I'm not going to go into anything like the Bellman equation or any math in general. We leave that for live interactions based on how the whole curriculum unfolds. But yeah, that's reinforcement learning. Yeah, thank you.